Right, we're going to have a look at a few reactions of metals today. And the first one I really want to do, I'm going to use sodium for. And it's showing the reaction of a metal with oxygen. I'm not going to burn it because that would be absolute suicide for myself. But what I'm going to show you is this piece of sodium that's been under oil, so it shouldn't have been exposed to any water or air. Well, actually, air can dissolve in oil because it's what we call a non-polar substance, and this is a non-polar solvent, the oil. So it's actually been able to react with oxygen in the air. And you can see that it's white on the outside. That chemical on the outside is actually sodium hydroxide. Now, I wasn't going to show you this shiny stuff yet. To prove that actually this isn't what sodium looks like, I'm going to cut through it. I hope it doesn't break, but it does just cut. See, I'm not a chef, I hold the knives totally wrong. And we will see that it is indeed very lustrous. But even while I'm holding it, it's starting to go white. So it's starting to actually oxidize already. So this is something that happens to all metals, but it's just the rate of it, which is different for different metals. So sodium happens really fast because it's high on what we call an activity series, whereas something like lead, for example, if I cut lead, it then takes forever to, well, not forever, it takes a very long time for it to go quite dull again. So I'm going to show you quickly what that reaction looks like by writing it up on the board. What we've got there, just very quickly, is sodium, and sorry, I think I said hydroxide, I mean oxide of that. Sodium plus oxygen is turning into the white stuff, and the white stuff on that is sodium oxide. Now if I put that sodium oxide into water, it turns into sodium hydroxide. So the moisture in the air will also be making sodium hydroxide on there. But if you were to do this as, what's the reaction between sodium and oxygen, it's just the oxide, because of course there's no hydrogens in here to make the hydroxide. You need to be able to do a balanced equation for this as well. So we should recall that sodium is Na. Oxygen is not O, it's O2. It's a molecule, it's not just an atom. As an atom it would be unstable, so like that it would be very unstable. So we say O2 because that's how it exists. It could be O3, what we call an allotrope of it, which is ozone. I hope not, because if there's too much ozone here, you'll be dying, and so would I. Because ozone, although it protects us from UV, is actually a poison. It's that funny smell that comes off heaters and other electronic things that you smell. You can often smell, and sometimes even taste, ozone. It's a funny smell, but that's in low concentrations, so don't worry. But it shows you how bad it is for you if you are sensitive to it. Now sodium becomes sodium plus. Oxygen becomes the oxide ion, so O2 negative. So using our little drop and swap thing, so I've got Na plus, O2 negative, they don't cancel out. I'm going to need to move the 2 from there to there to make it Na2O. Well, I can automatically see that that's not balanced. 2 oxygens, 1 oxygen. 1 sodium, 2 sodiums. Alright. I'm going to balance the oxygens first because I think it's an easy way to start. So I'm going to have 2 sodium oxides so that my 2 oxygens have got somewhere to go. That now gives me twice as many sodiums because we've got the 2 sodium oxide. Actually, what we call 2 moles of sodium oxide. So now I've got 2 sodiums inside that and 2 of them, so 2 times 2, 4. So it's a big 4, not a little 4 down here, a big 4 to balance that. So what do I need you to know? Well, you're not going to be playing with sodium in your internal because I'm not that brave to let you. So you need to know what the general equation is so that no matter which metal I do get you to work with, if you put it in a flame, because flames will accelerate the rate of reaction, if you put it in a flame and you see something change, so you see the oxide formed, you can write that equation. So what we've got here is the metal, plus O2, you don't have to write the word oxygen, you can write O2 for the word oxygen, makes the metal oxide. Using your iron table, you should be able to work out what the formula of that is and then balance it. So what we have also is a general equation, metal, sorry, red pen, don't like that one. Metal plus oxygen goes to metal oxide. Now, when I was your age many moons ago, I remembered it as O2 rather than oxygen because then I was never going to make the mistake and just put O there. So that would be my hint to you. Metal plus O2 goes to metal oxide is the easiest way to remember it, so you don't make that very easy mistake. Right, well that's with oxygen. It's a bit boring. Yeah, it's gone white, big deal. Should we make it a bit more exciting? Okay, what we're going to do now is I want to get rid of that big chunk because I'm not that brave. And I like my job. So that's going back into the oil. What I am going to do is I'm going to cut that little bit up a little bit smaller. Now, here I've just got tap water. I should use distilled water, really. I've got a chemical called phenolphthalein, which is one of our indicators we use in our acids and bases topic. And if I put it into water, look what happens. Okay, nothing. Absolutely nothing. Which is good. It's meant to do nothing. Because this stuff here will only change colour if there is a base present. Actually, more specifically, an alkaline substance, which means a soluble base. So I'm going to see if this, I've predicted this is going to make a base, because that's a base, so maybe when sodium reacts it makes a base. So I'm going to predict that's right. So now we're going to put sodium in water. And as I say, I'm not quite brave enough to put even this much inside. Yeah, it's about the same size as my thumbnail, which is about all we need to use. So we'll get that one out of our way. Well, out of our way. I'm going to put this to the other side of the water. And I'm going to put a screen over the top. Alright, now everyone's got their safety goggles on? Yes? Good. Okay. Here's the fun part. Aim it towards me, not you. And see what happens. Still not happy about the size of it. Sorry, I'm making it a little bit smaller. Yeah, I know you guys are sad about it, but I really don't want... It's quite thick glass with perspex really, but it's still... I don't want shrapnel. Okay. Oh. See why I made it smaller? Okay, that smoke is pretty much just steam. Okay, it's a highly exothermic reaction. We can actually see some white powder up the top here. Pardon me. Breathing water's not that good for your lungs. So we've got some fire, but we've got sodium hydroxide collected there. Now, just going to check that's cold enough. Yep. If I lift this off, I'm hoping. It hasn't really. I've had so much water on there, but it hasn't really worked. I don't think it's gone alkaline enough. Oh, it has. Sorry. So if I mix this, there's still some bits in there, but that's all right. Okay, it hasn't. This stage of my experiment hasn't worked particularly well because of the small amount of sodium that I used. Pardon me. So in here we've got. Yeah, probably should have left the lid on for a bit longer. It is slightly pink, but it's hard to see because of the blue container. So I'm going to ask you to trust me on that one. That this solution in here. Actually, let's see if we can do it this way. See if I can actually show you that it's alkaline. Yeah. There we are. That was a smart way to do it, wasn't it? Okay, if I hold it up there, you can see that it is pink. Okay, and it wasn't pink before, so we know that a base has been made. Right, so the last thing I want to show you is, again, using sodium as our cool example because it blows up, what we've actually had. So again, we started with sodium. This time, though, we didn't react it with oxygen. We reacted it with water. And again, I'm going to get into the habit of writing the formula because it makes the next step a lot easier. So rather than writing oxygen like a D or water as a word, I'm going to write H2O. Now, it could make sodium oxide. That could be what it makes. But I'm going to tell you right now that it doesn't. Okay? It makes a chemical that we use in the lab a lot, and that is sodium hydroxide. But that doesn't burn. So there must be something else made that burns. What burns the lovely yellowish flame like?
Hydrogen.
Awesome. It's actually more a pinky yellow flame. And it does. So we must have hydrogen. Again, I'm going to write H2 rather than hydrogen, because hydrogen as a gas is H2. It stops me making a silly mistake. Right, well, let's look at that the way we did before. This will be our last thing before we stop and do another one. So sodium plus water goes to sodium hydroxide plus H2. So I might move that in case we need to balance that. Right, well, my hydrogens look pretty good. Sorry, not hydrogens, my oxygens look pretty good. One there, my sodiums look pretty good. One there, but my hydrogens don't. You'll notice there's an odd number over there. That's a bit of a problem for me. So it means I really do need even numbers on both sides. So what I'm going to do is I'm going to find what's the lowest even number I can get to over there. Half's not over. 4, cool. I can have 4. I like that better. That's a much better even number.
Half isn't a number.
Oh, I see.
You could put half in H2 and it would still work.
No, because then I'd have
Half
you
of
3 versus
have
1.
half in H2.
Oh, okay. You're actually right, because when we, but not in this example. Okay, so I can get to 4. How can I get 4 over there?
Add something else.
Yeah, I need 2 of something, don't I? So 2 sodium hydroxides. And that means to get this to 4, I need 2 of those, don't I? Well, that's really convenient because that doubled my amount of oxygens and it did it on both sides. So that is really convenient. So is my equation fully balanced?
No.
What's not balanced?
Sodium.
Sodium. Cool. How many sodiums are in 2 sodium hydroxides? 2. So let's go 2. All right, let's have a quick look at our general equation so that you can apply this to other things like iron oxidizing or aluminium oxidizing or zinc oxidizing, etc. How do you think we'd write it as a general equation? Metal, I like that as a good start. I'm starting with metal. Plus H2O, I like that too. Good.
Metal hydroxide.
Good, metal hydroxide.
Plus
H2.
Brilliant, plus H2. Now you've already met the reactions of acids, and there's no way on Earth I'm going to put sodium in acid if it was that reactive in water. Okay? I like living. So, we're not going to do that one, but also you've met the reaction of metals with acids before. That is the third of the types of reactions you need to be able to write general equations for and examples for. Today it's going to be aluminium, but only if it reacts. If it doesn't react, don't write an equation for it. Magnesium, same thing. Okay, if it reacts, cool. If not, don't write an equation. Lead, by the way, strongly suggest you sand off the lead first. This is pretty old lead, so it's oxidized already. And calcium, now you can't sand off the calcium. Just trust that whatever layer is around it will dissolve off pretty fast when you put it in water or you put it in acid. Alright? What you're trying to find out is whether these react in cold water or not. And the best way to do it is to do it in a test tube with some phenolphthalein. If the phenolphthalein changes colour, it's reacted. Okay? Because that tells you it's made, it's oxide or it's hydroxide. If it doesn't, and you don't see any bubbles or anything like that, it's not worked. So if it doesn't work in cold water, try it in hot water. Okay? Now there's a jug down the back you can use for that. Do the same thing then for acids. Alright? See if they'll react with acids. Now you're not allowed to heat an acid directly. That's a big no-no. So what you do is you make a water bath, which looks like this. You have a tripod over a beaker, again some hot water, and then get that boiling. Turn the flame off. Put your acid and metal into your water bath and see if it reacts. If you keep the Bunsen burner going, you'll get a false positive because it makes the acid inside the test tube bubble. And so you go, oh, there's a reaction. And this is where people often go wrong in the internal. They keep the Bunsen going. They go, it's reacting. It's not. The acid is boiling, which is actually a big no-no. We don't like to boil acid. It tends to be bad for us. Right? So just be aware of that. Turn the Bunsen off, then put your acid reactions in there. So if they don't react in cold acid, try putting the acid in the water bath. Alright? So that's your investigation for today and tomorrow. You are going to tell me, basically, which of these react with water. If they don't react with water, see if they react with hot water. Which of these